Now, the topics that we shall be covering is nuclear energy or energy from nucleus. Under this topic, we shall go through nuclear fission and nuclear fusion. So, in this lecture, my purpose is to cover nuclear fission first, and then, if time permitted, we shall cover nuclear fusion. Nuclear energy or energy from nucleus. Now, nuclear reactions involving nuclei more than 170 constitute nuclear fission, and nuclear reactions for nuclei involving mass number less than 30. Nuclear fusion. For mass number less than 30, there is nuclear fusion. For mass number more than, if A, for nuclei having mass number more than 170, it is the fission reaction which is considered. For nuclei mass number less than 30, nuclear fission reaction. These are the two, there are two distinct ways of obtaining energy from the nuclei. One is nuclear fission and the other is nuclear fusion. So these are the two ways. Nuclear fission is heavy nucleus splits up into two smaller nuclei, liberating a large amount of energy. Liberating a large amount of energy. Liberating a large amount of energy, for example, atom bomb and then nuclear reactor as well. Nuclear reactor is a controlled nuclear reaction. And next is the fusion. This is the case of fusion. In case of fusion, now two smaller nuclei, they come together. We have predicted or explained nuclear fission and fusion on the basis of packing fraction and nuclear binding energy curve, particularly the nuclear binding energy curve. Now, together form large nuclei, releasing a large amount of energy, for example, hydrogen bomb or fusion reactors. They are the application. Hydrogen bomb is destructive application, and fusion reactors, so Russians have tried it. Fusion reactors is a constructive application. Nuclear fission. In nuclear fission, a phenomena in which excited heavy nuclei splits into two smaller nuclei of nearby comparable masses is called nuclear fission. So in this part, we are dealing with the basic definition of nuclear fission. This is nuclear fission. Excited heavy nuclei. Excited heavy nuclei, note down, excited heavy nuclei. So let us see this in diagram. Slow neutrons, here we have got slow neutrons. Slow neutrons they attack, they bombard or they strike 92 uranium 235 in nuclei. It splits up into 36 krypton 92, 51 barium 141, and these are the neutrons liberated in the fission process. Neutrons, this neutron and this neutron. 3 neutrons are liberated in the fission process. Now this reaction is one possible reaction. Now what we have to do, we have to just conserve Z and A. And there will be a large number of possible reactions, but only a few will dominate. Now, when uranium is bombarded by slow neutron, nucleus gets excited, capturing slow moving neutrons, and then splits up into nearly two equal fragments, along with the emission of 3 neutrons further. So this is the basic reaction for nuclear fission. This is 92 uranium 235 attacked by neutron. We get 92 uranium 235 excited nuclei or compound nuclei. Now it breaks up into 56 barium 141 plus 36 krypton 92 plus 3 neutrons plus roughly 200 MeV energy. So this is what do we get from it. And now total amount of energy released. Total amount of energy released per fission reaction is 200 MeV. This is called nuclear energy. Out of this energy, 5 MeV is carried by 3 neutrons produced in each fission reaction. So 15 MeV is carried by neutrons, and the remaining energy is available to be used as heat or something else. Theory of nuclear fission. There is a liquid drop model of theory of nuclear fission, and what that theory says, this is a neutron, this is uranium, uranium 235. Now it has started oscillating. Uranium 235 has started oscillating like this, and here it splits up. And this is just this theory, this diagram has just been introduced from interest point of view. Neutron bombards 92 uranium 235, then compound nucleus is formed. This neutron is captured by this uranium 235, and then it starts oscillating and becomes unstable and finally splitting up into two main parts and then 3 neutrons. Fission products. Now all the nuclei did not break up into barium and krypton as we have shown in the previous reaction here. This is one of the possible reactions. A large number of other reactions are possible. What we have to do, we have to just conserve Z and A. All reactions which can conserve Z and A and energy and then angular momentum and then spin and parity. Basically these two, Z and A. There can be large number of reactions. So fission product will not contain only these two nuclei. There will be other nuclei as well. And when the yield of the fission product uranium 235 was analyzed, it was found that fragments corresponding to this was the final output of the fission product. First we see on x-axis we have mass number, and here we have got yield. Now what was observed? This is the peak. For example, this is the peak and another peak is this. So this peak corresponds to 100 mass number and this approximately 150. Now if we analyze this, then we can say most of the uranium-235 nuclei, they split up into nuclei having mass number near 100 and 150. This is. So there is a one peak is near 100, mass number 100. Other peak is near mass number 150. So these two yield peaks, they tell us directly that these are the dominant mode of splitting a nuclei. What are the dominant modes? That one nuclei will be of mass number near about 100, other may be near about 150. So there are two dominant modes. For example, if I say one product will be having mass number approximately 100, other product, say I can call it Y1, it will have mass number 50 plus 3 neutrons, like this, 3 neutrons. So these two products, when the whole yield was analyzed, they found that maximum number of nuclei corresponding to mass number 100 and mass number 150, and concluded that the most dominant mode of nuclear fission of uranium-235 contains these two mass numbers. So this is the most probable reaction. Since very massive nuclei have many more neutrons and proton, fragments have a considerable excess of neutrons, several of which are released in free space. We don't need to go through it. I have just told you the crux. Release of the neutron per fission. This is a very important factor. Average number of neutrons released per fission were estimated to be Na. Out of this, 99.36% of neutrons are emitted within 10 raised to power minus 14 seconds, called prompt neutrons, and others are emitted after some time. These are called prompt neutrons. Others are known as delayed neutrons. More than about 99.36% of the neutrons are emitted within 10 raised to power minus 14 seconds, called prompt neutrons. These are called prompt neutrons. And then we have got delayed neutrons as well. Fission of their elements. It may be pointed out uranium is not the only element which can undergo fission. All elements above Z is equal to 85 undergo fission with suitable energy of neutrons. Energy per fission. Now energy per fission has been calculated by using formula E is equal to mc square. So what was done? Sum of the masses, for example, this is the famous reaction 92 uranium-235 bombarded with neutron. We get barium 141, krypton 92 plus 3 neutrons. Now, numericals of this nature appear repeatedly in your board examination as well as in your NEET and JEE main examination. Now, what we observe is that sum the masses of reactants and sum the masses of products and find the difference, and total mass before reaction is 236.044398 AMU. Total mass after reaction is this, note down. I'm just giving you the final figure. This is total mass of uranium and neutron. This is total mass of barium, krypton and 3 neutrons. And loss of mass is this much. And then you just multiply it by 931. 1 AMU is 931 million electron volt. And if you multiply this by just, this is 0.2153, you just multiply it by 931, then you get energy in MeV. So this is roughly, I can say 1/4 or 1/5 of this. 1/5 of this, roughly 200 MeV. So you will have also to solve numericals, and I strongly recommend that you should solve numericals of this nature, where first you find the mass defect, then multiply by that mass defect by 931 MeV to get the final answer. So in this way, we also talk about the energy produced in nuclear fission. And there is one more thing, that is nuclear chain reaction. This is a very important factor, nuclear chain reaction. And before going through nuclear chain reaction, there are two ways of calculating energy. This we have calculated energy by the process of mass defect. I will write here. There are two methods of calculating energy. This is important from competition point of view. One is by finding mass defect. Other is by calculating, you can also find it from binding energy. If you know the binding energies, then you can also calculate it from binding energy. There is a binding energy method. In binding energy method, binding energy of all of them is given, and you find the differences between binding energies, and then you get the final energy release. For example, uranium. I will just pick up a few points to illustrate this. Uranium has binding energy 7.6 MeV. And now fission products, these two fission products have a mass number 72 and 158. Average binding energy for those two products, average binding energy of the products is this, and average binding energy of uranium is this. We found just the difference between these two energy, and then there are 235 nucleons, and we multiply it by 235. Then we get 200 MeV. Note down the method of calculating energy first from mass defect. In case of mass defect, you find the difference between the mass of reactants and products. This is a mass defect method of finding energy. There is another method of finding energy released in the nuclear fission reaction, that is, find the average binding energy of the products and then the binding energy of uranium, find the difference between them, and that difference will be for one nucleon. And now just multiply it by 235. You will get the exact value of the energy released. So these are the two methods. They are useful when you will be doing numericals. So in brief, we have gone through first energy released from the nucleus. This was the topic. If you want to get energy from the nuclei with mass number less than 30, then the process of nuclear fusion has to be taken into consideration. Nuclear fusion is the fusion of two lighter nuclei to form a stable nuclei. Energy is released in this reaction. And the second is, if you want to get energy from heavy metals, then we have to follow the process of nuclear fission. And process of nuclear fission is possible for all the nuclei if they are suitably bombarded, having atomic number more than 85. So huge amount of energy is released in this processes. Energy released in fission process of uranium 235 is 200 MeV, and the energy released in fusion of neutrons to get helium is about 17.5 MeV. So in fusion process, energy release is less than fission if we think only total energy released. But energy released per nucleon in fusion is much larger than energy released per nucleon in fission. In my next lecture, we will study the nuclear chain reaction. Thank you very much. Before finishing this lecture, I will request you to comment if you don't like the video and share if you like it. Thank you very much for being with me for 22 minutes.